Hello everyone. It's a pleasure to present our work, secure provisioning of OPC UA devices here at the Safety Meets Security conference. As you can see by all the names, it's not only my work, it's also the work of my colleague Sören Finster and David Meyer and Florian Patzer, who are from the Fraunhofer IUSB. They are our project partners in the BASIS 4.2 project, which also partially funded this work. Okay, so first, as some of you may not be familiar with OPC UA, let me briefly introduce you to the topic. So OPC UA stands for Open Platform Communications Unified Architecture. It's an application layer communication protocol for industrial systems. So traditionally, industrial systems communicated using proprietary protocols, often field bus protocols. But nowadays, everything converges more and more towards Ethernet, and OPC UA is a protocol on top of the network stack that is cross-platform, open, and provides a service-oriented architecture. It's considered to be like the protocol for the industrial Internet of Things, so particular for all kinds of field devices. OPC UA has two modes, a client-server mode, which is the main mode of the protocol and also the mode on which this talk is focusing. There's also pub sub-mode that allows devices to subscribe to values that are broadcasted by a publisher, which, however, uses a completely different security mechanism. Yeah, and as already said, OPC UA has built-in security capabilities. When you connect to a device, you can choose to use either no security or security, and then your communication is authenticated and encrypted. And also there exist techniques to do user authentication, give them access, different access rights on the devices. And in this talk, I'll be focusing on the lower part here on the right picture, so on the communication protocol and on the field devices. So now that you know OPC UA, what is provisioning about? Provisioning is about transforming a device from its initial state to the operational state. So a device gets shipped to the operator from the manufacturer, and then the device needs to be checked for authenticity, needs to be checked for manipulations. You need to configure the functional parameters. You then also need to configure the security parameters and also the infrastructure so it can securely communicate with the new device. And finally, after provisioning, the device is in operation and you can use it for daily business. And in this talk, we will be focusing on the security aspects of provisioning. So configuring all the security parameters and the infrastructure. So yeah, what is needed to securely provision a device in OPC UA? OPC UA security is based on mutual authentication with certificates. So this means that each device has its own key and a certificate for that key. And also each device has a so-called trust list that contains certificates from communication partners, basically. And then when devices establish a communication, they mutually exchange their certificates and verify the received certificates based on the certificates in the trust list. The certificates in the trust list can be self-signed certificates, but can also be CA-signed certificates, which makes the management of the certificates a bit easier. So you have to store less certificates in the trust list. And this mutual authentication with certificates that provides rather strong security guarantees, but it also means that you need to deploy these certificates initially and also manage them during operation. And for the purpose of managing OPC UA certificates, the OPC Foundation, which best specifies the OPC UA protocol, they introduced the so-called global discovery server. Here's a short introduction to the GDS, specifically mentioning all the security features of the GDS. So the GDS is basically a server, so additional infrastructure that you put into the network. It has two interesting features for certificate management. You can modify the trust list of devices. So this means you can add, update, and then remove certificates there, which is required when new devices come to the network or old devices leave the network. You can also, with the GDS, issue new device certificates, which is required when devices change their IP or DNS. So the certificate contains the IP address and the DNS name of the particular server or client, and that is checked when you establish a connection. And of course, issuing new certificates is also required when the old certificate expires. However, the current specification of the GDS disregards all the initial trust. So there's no provisioning process defined for the GDS. And it's only specified that GDS and the device, they could just accept the first certificate that they receive to establish an initial connection. And afterwards, the GDS supplies devices with the actual certificate. But this means that in the beginning, we have no authentication. An attacker can hijack the connection during this initial step. So secure provisioning is still an open issue in the current OPC UA specification. So this is why we then started to investigate secure provisioning solutions for OPC UA. We did that in 3 different directions. We looked into actual OPC UA products on the market, mostly gateways and PLCs. With the hope that they have some interesting provisioning approaches that attempt to solve this problem. We looked into academic works and upcoming standardization efforts, and also looked into solutions from the IoT domain to also find out whether they can be applied to OPC UA. But let's start with the state of the art. So how OPC UA provisioning is done in actual products on the market today. And what we found out there was actually a bit disappointing. So we found no real OPC UA provisioning solutions. Instead, either the provisioning problem is ignored, so it's not specified how to establish this initial trust, and it's up to the user to manually configure the certificates and the trust list, or trust on first use is proposed, which is also shown here on the slide. And so this is the approach where devices just initially trust a new device when they communicate with the device, with the device for the first time. And what we found in products is that they typically come with a self-signed OPC UA certificate that is generated when the device starts for the first time, or when the device changes its IP or DNS name. And also devices, they typically implement a web server that allows to configure the device, including also the OPC UA certificate settings. And the TOFU approach that is often proposed, that works by establishing trust when client and server communicate for the first time, that typically requires manual steps to establish this trust. So what is typically done is that, for instance, the user is shown a pop-up where the user has to manually set this certificate as trusted. Or what is also done is that when you connect with the client to the server and the server does not trust the client, then the certificate is put into the untrusted or quarantine folder, and then the user can manually inspect that certificate and move it to the trusted folder. And from then on, the device that has a public key that corresponds to the certificate that is put into the trusted folder, this device is then trusted. But for the user, it's actually quite impossible to manually verify whether a certificate is trustworthy without having any further information. So how does the user know when he sees a certificate that the device actually has the key that is shown in the certificate? So that is shown in the certificate. So this is why users typically just ignore that, and this allows an adversary to then perform man-the-middle attacks, so to undermine all the security guarantees that are provided by OPC UA actually. So this slide illustrates how the process of this trust on first use approach typically looks in practice. So what you typically do is you connect to the web server of the device. The web server typically uses an HTTP and not HTTPS, because HTTPS, it works well for the internet, but not in your internal network, because there you again need to have a certificate that is valid for the URL or for the IP address that someone needs to issue, and that also needs to be distributed to the browser beforehand. So this is typically not done. So there is already the first attack vector for an adversary. He can just hijack the connection here and give the user a rogue certificate. But nevertheless, the user typically takes the certificate, gives it to the client. The client will then attempt to connect to the server, but since the server does not yet have the certificate of the client, the server will reject the communicating with the client, and the certificate lands in the current folder of the server. The user then connects to the web server again and manually marks the certificate as trusted. But here again, attacker could just connect with the rogue certificate to that server, and the user has typically no means to verify whether this certificate actually here is from the client. But eventually, when the user presses that button, both devices are then connected. So it's quite apparent that there are issues with this approach. First, of course, it's not secure. There are two steps that allow an adversary to perform man-in-the-middle attacks and impersonate the client towards the server, or vice versa. But second, this is also very complex and requires high manual effort. So even if you know exactly what to do, it requires you 2 to 3 minutes to provision a device. And most engineers who install and configure the devices in the field, they are not familiar with OPC UA security. So it would probably require them even more time to do it. And the complexity is also a reason why OPC UA security is often misconfigured. So there's actually a study from last year that analyzed OPC UA servers that are exposed to the internet. And that study shows that 92% of the internet-facing OPC UA devices have misconfigured security. It is either disabled, so the security profile none is used, which provides no security, or deprecated cryptographic primitives are used, or certificates are reused just for convenience. So to summarize, an engineer can either enable security, but then it's hard and complex for him to configure, or the engineer disables security, which is then easy to configure, but then an attacker can just compromise all connections, and there's nothing in between right now. However, what I would like to show you now are two promising solutions that we identified which aim to solve this gap. They are much less complex than manually configuring like perfect mutual authentication, but provide good enough security also for. They maybe have a bit less. They maybe provide a bit less security than the state of the art, but provide good enough security for typical use cases. And the first solution that I'll show you is called the provisioning GDS, which is compliant to the existing OPC UA specification. And the second solution that I will show is the OPC 10021 draft, which is an upcoming standard by the OPC Foundation. So let's start with the first solution, which is actually the scientific solution, because it has been proposed by our project partner, the Fraunhofer ISB, and it has been published last year at the EDFA conference. The idea is that the GDS is not implemented as a server in the internal network, but instead the GDS is implemented as a small handheld device. A small handheld device that allows the operator to directly connect the GDS to the device that should be provisioned. And the GDS then uses the previously described trust on first use approach to establish an initial connection, and uses this connection to transfer OPC UA certificates to the device. As described, TOFO is not very secure, but as the provisioning GDS is directly connected to the device, an adversary cannot just sit here on the wire and perform man-in-the-middle attacks. So the security here comes from the proximity between GDS and device and the direct connection between them. And then in a second step, the provision device is connected to the internal network, where it uses the certificates provided by the GDS to communicate securely with all the other devices in the network. There are many variants also to this approach. For instance, you can have a second stationary GDS in the internal network. And in this case, the provisioning GDS issues only ephemeral certificates for the device to establish a secure connection with the stationary GDS sitting here, and the operational certificates that are used during the lifetime of that device at the operator, they are then provided by the stationary GDS. The advantage of this approach is that it's compliant to existing OPC UA standards, in particular the OPC 10012 standard that describes the GDS. Disadvantage is that it builds upon the GDS, which is still not that widely available. There are still some devices on the market that do not support GDS push-pull model required to obtain certificate from the GDS. And also there are not that many GDS products on the market, but the situation is getting better and better. More and more GDS implementations are available, and they are also increasingly mature. So now to the next technique, which actually comes from the OPC Foundation itself. It's the OPC 10021 draft, in whose standardization we from ABB are also involved. The idea is that you produce devices with onboarding certificates that are used by customers to authenticate the device later on, at their operator. In detail, here each manufacturer has its own certificate authority and produces devices with a unique key pair, and then issues for that device a so-called IDEF ID certificate based on the IEEE 802.1 AR standard. It's basically like a birth certificate that is valid throughout the entire lifetime of that device. And also the manufacturer issues a device identity ticket that contains further information about that device. Those CA certificates are then distributed basically through to all actors here through a secure out-of-band channel. How the secure out-of-band channel looks like is not further described in the standard so far, in the draft so far. Each actor in the supply chain also maintains a CA, verifies the authenticity of devices based on the CA certificates, device identity tickets, and IDEF ID certificate when they receive the device, and they then extend the ticket, which also includes adding a signature to that ticket. And this way, the authenticity of the device can be verified throughout the entire supply chain. For instance, here the machine builder can assemble a machine that consists of many devices, then issues a ticket for that machine that authenticates all devices and says they belong to the machine. And finally, also the operator can authenticate received devices and verify the entire supply chain. This slide here shows a simplified illustration of OPC 10021 with only 2 actors, so how it can be implemented in practice, basically between a manufacturer and an operator. Yeah, as shown on the previous slide, OPC 10021 typically also involves more actors. The process is that here the operator orders a device from the manufacturer, then receives from the manufacturer the CA certificate, for instance, through a secure connection that is authenticated using HTTPS. This certificate is imported into a register tool at the operator. The manufacturer then produces the device, issues a ticket and a certificate for the device. It is shipped to the operator. The operator then executes an interactive protocol with the device to verify the device authenticity based on the ticket and the CA certificate. And after the verification succeeds, the operator then establishes a secure channel with the device and uses the well-known GDS to install proper OPCA certificates on the device. The advantages are that trust can be managed throughout the entire life cycle, involving all actors in the supply chain. Not only the operator is here able to verify the authenticity of the device, all actors in the supply chain can do that. And also the standardization enables interoperability between all actors. Disadvantages are that GDS and IEEE 802.1 AR certificates, they are both not that widely available. And in addition, this draft is rather complex for the manufacturers and involves a high PKI management effort. So you somehow shift the effort and complexity for OPC security from customers to the manufacturers. Besides the state of the art and the 2 solutions that I've shown, we have also investigated further approaches, which are summarized here on the right side. In gray, the solutions that I described are shown, and in white, solutions we haven't touched because of time in this presentation. We evaluated all the solutions based on 4 bigger blocks of criteria, which are the device requirements. So what devices need to implement to use the provisioning solution, infrastructure requirements. So what infrastructure do manufacturers, operators, etc. require to use the provisioning solution? Usability, so how easy and scalable is the solution, and security, so what security guarantees does the solution provide? And what we found out is that, as said, existing solutions provide an insufficient level of security. Emerging solutions provide much higher security guarantees and usability, basically by relying on cryptographic trust anchors. However, shifting the effort a bit more to the manufacturers. In general, there's no solution that is completely superior to all other solutions. All have their pros and cons, and typically, there is a trade-off between usability on the one hand and on the other hand, requirements on devices and infrastructure. And topics for future research we identified are transitional solutions that enable incremental updates to emerging solutions, emerging standards, so you can step-by-step move towards a final, really secure and convenient solution that, however, requires high costs on the infrastructure, for instance. And another direction are establishing initial trust between all involved actors, which is more about policies and procedures. What I've shown in this presentation is also part of the survey paper that we recently published. Also, the table shown on the last slide comes from that paper. So when you want to know all the details, you can look into the paper. It's called On the Security of IoT Deployments, an Investigation of Secure Provisioning Solutions for OPC. It has been published in IEEE Access Journal, which means that it's freely available for everyone. Contributions I've already summarized on this last slide. And As said in the beginning, this work was partially funded by the BMBF project Basis 4.2.